The wave equation then. Let's have a look at this, or the wave function. Something that we use an awful lot. And if we think about where this wave function comes from, we can hopefully see how these ideas of trigonometry really come in useful. We consider something rotating, so this green dot here that you've got, rotating around, generally by convention anti-clockwise as it goes around a circle like this, is what we're considering. And so we're just going to define a few things about it. The first thing is that unlike linear velocity, which is the velocity of something travelling in a straight line with velocity v, we now consider something rotating with what's called an angular velocity. And we use omega to represent angular velocity. This symbol here, omega. Looks like a W, but it's a curly W. Hopefully you've seen that symbol before. Omega represents the angular velocity of something by convention rotating anti-clockwise. So if I have a negative omega, that means it's rotating clockwise. So if we consider this thing rotating, here it is. At any instant in time, say here or here or here or here, I might be interested in how far it's moved up and down this y-axis. So we consider that as time's going by, let's say it's reached this point here, it's moved this far along the y-axis. An instant later, here, it's moved this far along the y-axis, and then it reaches the top, and then it starts to come down, so it comes back down the y-axis like this. So you can see that if I'm only considering the y direction, that y direction is going to be moving up, and then down, and then back up again. So if I put that on a graph, with time, it will be going up, and then up, and then down, and we end up with something like this. So this wave function is describing something as it rotates, but it's describing just the y direction. And that turns out to be really useful, because I might be wanting to consider this rotation producing a voltage. So I could represent voltage on this axis against time. So this amplitude is actually giving me the voltage as time goes by in an AC circuit, for example. Or I might be considering something literally rotating, a mechanical device, a cam and a rotating flywheel or something like that. Well, then again, I would be considering maybe just how far along in a slot in the groove some sort of slider is moving, only in one plane, in say the x or the y direction. So again, I'm just interested in this movement up and down, not the rotation. Again, this describes it. So it's really useful to be able to study this wave function, or wave equation if you like, in detail. At the moment, if we look at this, this is angle against amplitude, but often we use it to represent time. So this is often time along here. But we'll leave it as angle for now, because we can talk then in terms of radians. Already we've talked about this idea of the radian representing 2 pi radians in a complete turn. So a complete turn of this, if we consider just the y direction, complete turn will take us up to the top here, down to the bottom here, down to here, and then back up to there again. So one complete turn takes us to here, 2 pi radians. So half a turn, a quarter of a turn, pi over 2 as we said already, 3/4 of a turn, 3 pi over 2. So that's how we have, and if we're working in radians, this can represent a time. So if I'm measuring time along here, 2 pi, pi is about 3.14, so 2 lots of 3.14 would be 6.28, 6.3 seconds would be the time. So I can use the angle, if I'm measuring it in radians, to give me a figure, a time, for example. So we tend to only measure angles in radians when we're talking about the wave function. When we talk, as we'll see later, about the idea of phase difference and phase angles when we're talking in electricity, which I think you'll be doing with Mike Bex next semester, well, then he might want to convert that phase angle into degrees, because we sometimes think of it in terms of degrees, 90 degrees phase angle, for example. But if you're working with it, you'll be working in radians, and then at the end maybe converting to degrees. Okay, so let's think about a few more things to do with this wave function then. Well, the frequency of this thing is the number of turns, complete turns, divided by the time. So say this thing rotates 5 complete turns in 5 seconds, then 5 divided by 5 is 1. It's rotating at 1 cycle per second, or 1 hertz. So if I divide the complete turns by the total time taken for that, then I've got the frequency. So there's a little formula that we use all the time to get the frequency. We can think of the number of the turns as n times 2 pi, where 2 pi is 1 complete turn, so n times 2 pi is the number of turns. So you might want this little formula as well, that the number of turns is 2 pi n. Is another little formula we often have in our mind, but it comes from the idea of frequency, and it's something we'll be using a little bit later on in the engineering science. Remember our definition of the angular velocity, omega? If we think about linear velocity, it's distance over time. Angular velocity is angle over time, this formula here. The angle I've turned through divided by the time taken for that is, so it's exactly the same definition as linear velocity, but instead of distance over time, it's angle over time. So this formula allows us to calculate the angular velocity. Another way of thinking about the angular velocity is if we think about 2 pi, remember, as being a complete turn, and the frequency being the number of turns per second. So let's say the frequency is 2 hertz, 2 cycles per second. That's 2 lots of 2 pi, isn't it? Because 1 turn is 2 pi, so 2 lots of 2 pi per second. So in other words, the angular velocity is just given by the frequency, the number of complete cycles per second, multiplied by 1 cycle 2 pi. So I've got that useful formula, omega equals 2 pi f. So there's a few little formulae here, equations that we use when we're talking about wave functions. We also have here, if we go back to this, hopefully you can see straight away that if I want to know how far it's gone up the y-axis, for example, I've got a right-angled triangle there, so r, sines, cosines and tangents are going to come in useful. If I know this angle, this is the opposite side of the triangle, so it's to do with sine. So the sine of the angle multiplied by the radius of rotation will give me the y slope, which leads to these ideas here. So the y, which is the distance up the y-axis, so this could be the voltage if we're measuring voltage, or distance if we're measuring a slider, equals A for amplitude. So amplitude is the maximum height of this thing. Let's look at the wave again. What's the maximum height that this thing reaches? It's the radius of curvature, radius of rotation, isn't it? If we think about that, what's the maximum distance we can go along the y-axis? It's this radius of rotation. And when you reach 90 degrees, then we're at that maximum point. So y equals A, the length of the hypotenuse, in other words, times by the sine theta will give us this distance y. From trigonometry, from the ideas of sine is opposite over hypotenuse. If we think of theta in terms of the angular velocity, we've already got that omega equals theta over t, so this formula can rearrange to give theta equals omega t. Then instead of theta in this equation here, we write omega t, we've got our wave function. Y equals a sine omega t here. So that's the basic formula for the wave function, y equals a sine omega t. However, we add this phi, or alpha sometimes, phase angle. What that is telling us is, it gives us the option to start not necessarily at 0. If you look at this part of the formula, and let t equal 0, that equals 0, then the sine of 0 is 0, so that means we start at y equals 0. In other words, we go back to here. When t equals 0, we're here. So we're starting at 0. What if we're on a rotation, or we're starting with a voltage, a fixed voltage to start off with, of this value? So we're not starting at this point, we're starting at this point, at some distance around the circle already. Well, then what we do is we add this angle. We add this phase angle, phi, to give us our start point. So this is just allowing us to start our rotation at a different angle other than 0. So sometimes we add this phase angle. So this is the full wave function. Y equals a sine omega t plus phi, or alpha. And it describes the position along the y-axis of a rotating vector moving with angular velocity omega and amplitude a. This amplitude a is the radius of rotation. Angular velocity is measured in radians per second, the angle I've gone through divided by, or per second. So we always measure the angle in radians. And there's a chapter which takes you through some questions to do with finding out a, or omega, or phi, or y, given some values that you can have a look at.